Alright, welcome to the NUPOC Video Study Guide number 10. We're going to look at question 8. We're going to look at the second part of that. Like we said in the last video, it's basically got three parts in this question. It's asking for a brief discussion of the Fourier series, the Taylor series, and some Laplace transforms. So the Taylor series, it's fairly straightforward in its definition, so I already have it written out here. Essentially what it is it's just a tool that we can use to approximate a function around a given point. So similar to the Fourier series, where we're using a function, where we're using the Fourier series as a tool to approximate a function sort of over all points, here we're just sort of expanding around one point in the function and expanding from that point to approximate the entire function. So the definition just looks like this. It's essentially, our function of x is equal to this infinite sum, where we have the nth derivative at a, which is the point where we're taking our approximation around, divided by n factorial times this term, x minus a to the n. So if we took this infinite sum, we would find that this equality is true, but in a practical case, we maybe only want to look at, say, the first 3 or 5 or 7 or whatever terms of this sum, and that will give us a good enough approximation in the area around A for our purposes. And so what you would do is you would take the first however many terms you wanted, and then you can plug in x, and the values of x would be sort of in the area of A, near A, and the more terms you take, the farther you can push your values of x from A and still have it be an appropriate approximation. So we would use this in cases where, say, we have some function and we are interested in that function in a certain area, in a certain operating point, perhaps. I can think of, for example, if you have a diode and you want to look at a certain, a diode has an exponential VI, voltage current characteristic, and for electrical engineers may be familiar with this. And if you're interested to know the behavior of that characteristic in a certain area, you can use the Taylor series to do an expansion in that area of the exponential and get a very good approximation without having to evaluate the whole function, which is really useful. A couple of caveats with this. Like with the Fourier series, we had the caveat that the function had to be periodic. Here the function need not be periodic at all. Like I just said, we use it on exponential functions all the time. But it needs to be infinitely differentiable if we were to take this infinite sum. But in the practical case, it needs to at least have as many derivatives as terms you want to take of the Fourier series. And also the function needs to be continuous. So what we would see, for example, if we had an exponential function, let's say, and we wanted to take, let's just kind of draw a quick little sketch here, and this is our exponential function like this. If we wanted to take, say, the first term, it might look something like this, some constant. Depends on where you want to take it. Say we're taking it about this point here. So maybe our first term goes like that. And then if we take a second term, it might approximate it like a tangent. And then our third term might do something like this. And then our fourth term might do something like this, right? And so in this area around this point that we're expanding around, we're taking the Taylor series expansion around, you can see after just a few terms of the series, we haven't approximated the entire function yet. It still diverges away from this point, but in this area it'll become a very good approximation after just a few terms. And just another note, if we take this expansion, if we take this Taylor series and we start expanding around a equals 0, so we start taking x values in this area here right around x equals 0, or well, a will equal 0 and we'll take x's just on either side of that. That would be what's called a Maclaurin series, so it's just a special case. And that's about it for the Taylor series. It's simply a tool that we can use to approximate functions that are not periodic but have at least several derivatives and are continuous.